just set the... All right, well, good morning everybody. Welcome to today's webinar. My name's Martin Atkins here at the Energy Research Centre at the University of Waikato. I'm joined here by Tim Wormsley, who's going to be my co-pilot today. I'd just like to thank ICA for sponsoring and helping us putting on these webinars. And just a reminder that this webinar is being recorded, and so it'll be available at some point in the near future for review and to have a look at again, as well as the previous webinar that James Neal gave a couple of weeks ago. Now, the other thing too is if you have any questions, feel free to use the software there to put in the question or raise your hand. We can we'll either answer the question as we go along, or we may wait to the end. We'll just see how it fits, and we may, if we need to, unmute you, and if you've got a mic, it may be easier just to ask the question over the mic. So we'll get going. Today's webinar is around really an introduction to beginning a pump systems assessment, especially with a focus on energy reduction. And so what we're going to talk about today is really why are pump systems important, where they fit into the grand scheme of things, the difference between a pump assessment and a pump system assessment, and the importance of really focusing on the system and not just the pump on its own. We're going to talk about some of the benefits that come from pump system assessments. And then what we're really going to focus on today is really the first step in beginning a program for pump system energy reduction, which is really a pre-screening exercise. And so we're going to talk about some of the ways to do that and where it fits into the bigger picture of an overall energy reduction program. We're going to go through an example of that, and then also go through an example of a fairly simple energy reduction method and go through some calculations just to give you an example. And this really is an introduction to keep that in mind, and we're going to build from here and go into more depth in future webinars later next year, early next year. And then also at the end, some additional comments, where to get some more information, and also where to from here. Okay, so pump systems, why are they important? Typically about 20 to 30% of a country's electricity demand is from the industrial sector, and that's fairly standard across most industrialized countries. It may be a little more, it may be a little less, depending on the mix of industries in the country. Around 5% of New Zealand's total power use is actually from pump systems. So not only industrial systems, but things like irrigation, municipal water supply, things like that. And so it soon adds up to be quite a large amount of our total power consumption. Now, it's fairly accepted estimate that around 75% of industrial pumps are oversized. And that's been shown to be true not only in New Zealand, but throughout the world. It's a fairly well accepted number. And so what that does is allow or provide the opportunity to stop oversizing pumps, but also to then reduce the energy consumption and also the maintenance. And we'll talk a little bit about that later around the link between energy and maintenance and reliability of pumps, and why those two things are linked. We're also going to talk about some of the common problems and some of the common solutions, and also why taking a systems approach when examining a pump system is beneficial. And it's really important to do that, because the cost-effective solutions really need to be tailored to specific systems. Okay, now some of you may have seen this before. I've certainly talked about it in the past. Back in 1996, there was a technical report from Finland where they evaluated about 1,700 pump systems across multiple sites and multiple industries. And with really looking at how efficient are pumps being used in industry. And what they found was very interesting. Firstly, the average pump efficiency across these pump systems was less than 40%, which is very low. Typically, you'd expect 60 to 90% as a typical pump efficiency if it's operating at the best efficiency point. 10% of pumps were actually operating below 10% efficiency. So there's huge room for improvement based on those numbers, and also the average motor efficiency was slightly less than what you'd anticipate. And what they concluded as to why this was so was really already sort of suspected, but it helped confirm what has been sort of known. The major factors were oversized pumps being specified too large, so usually providing excess head, and then the use of throttling valves then to overcome the fact that the pump was oversized. And from a maintenance point of view, the highest downtime had to do with seal leakage, which is actually related to the pump being oversized in the first place. And so it's likely that the same sort of trends are applicable across New Zealand as well. So for example, I know of a system in New Zealand at an industrial factory that had a fairly high variable flow rate, and 50% of the time the pump was operating below 45% efficiency, and it was a fairly big pump, and so it's likely that this is going to be true for New Zealand as well. Okay, so briefly, why are so many pumps oversized? And we've talked about this in more depth in the past, and we probably will do this again in the future, talk about why pumps are oversized and how to avoid them. But there's a few main things that generally come up each time. Usually the first one is that when the plant was designed, we want to future-proof the design, and so future expansion, production increases and things like that are often cited as to why a pump was oversized in the first place. Now often those never materialize, or they are at several years in the future, and so the cost-benefit analysis of doing that can be very quickly assessed, and most of the time it's the extra energy that you expend with the oversized pump doesn't justify having that size pump. You're better off having an appropriately sized pump to begin with, and then changing that in the future. There are some things you can do around, increasing the impeller size and things like that that may give you some flexibility. But that's often one of the factors that's cited. The second big one is around safety factors or anxiety factors, and really what they are is they really show the uncertainty in the design. Now, often they're appropriate to use some safety factor on some parts of the design. So for example, on the dynamic head or the friction loss in the system, there's a little bit of uncertainty there, but typically your flow rate demand is fairly well known, and so there's no need to apply a safety factor on that. But what tends to happen is if the design engineer puts a safety factor on, maybe a consultant or a supplier then puts an additional safety factor on because of this uncertainty, you can very quickly have a fairly oversized pump, and there are some major implications for both the capital cost and also the operating costs of that. The third one is that we often aren't spending the time and doing good system design, or there's a lot of uncertainty there around the design and what the pressure drop requirement is. Sometimes we're in a rush and we just want to make sure that the thing works, and we're less worried about longer term energy costs and things like that. If it's a replacement, typically a policy at many plants will be just replace like for like, and so there's no actual assessment on whether what's being replaced and put in is actually appropriate for the task. And if the original pump was oversized, then all you're doing is replacing it like for like, and you've not actually had any gain. So actually that's a good point to raise just here, is that if you are looking at replacing pumps, is to actually look and see if you actually have an opportunity to have an improvement there. Sorry, Paul, are you still getting me okay? All right, thanks. Okay, also we're risk adverse, and so we want to make sure our plants operate, and so making sure that the pump is going to deliver both the flow and the head requirement is important, and so we just want to avoid any risk. And many times energy prices, they can be seen as it's uneconomic to put the time and the energy into optimizing and getting the appropriately sized pump for the system and designing the system correctly. However, as we'll talk about a bit later, when you take a life cycle approach or a total cost of ownership, then the energy cost of operating a pump system is by far the biggest component there. Okay, so when we're looking at pump systems, we actually need to focus on the entire system, or take a systems approach and not just look at the individual pump alone. Now, the key question when starting an assessment or looking at a pump system is to actually ask the question, what is the purpose of the pump system? What is its function? And then another question to ask is, how efficiently does that system perform its function? And so there's a difference between the pump efficiency and the system efficiency. Now, the pump efficiency is basically, you can look on the pump curve and it tells you how efficiently the pump is operating, but it doesn't tell you anything about how the system is operating. So for example, you may have a pump operate at a very high efficiency, let's say 85%. However, if just after that pump there is a large throttling valve, or there's a bypass which is returning flow back, and that's unnecessary, then you have a lower system efficiency. The pump in isolation is operating very well, however, the system is not appropriately designed and operated, and so there's a low system efficiency. Now, some of the benefits from looking at the pump system, obviously, we're usually interested in energy savings. So we're trying to reduce the operational cost of operating the system. Typically, that's electricity. However, one of the things with an oversized pump is that you actually reduce the reliability of that pump. And so what you typically find is that you have a lower pump and system reliability when you have an oversized pump. That can lead to reduced downtime and increased costs as well. And so along with energy savings, there's also maintenance savings to be gained by looking at your pump systems and correctly sizing them. Also, especially at the outset, there's capital savings as well. If you do not oversize your pump, typically you may have a much smaller pump size. That leads to a smaller motor, as well, and so there's capital savings as well that can be gained from correctly sizing pumps and doing that properly. And we'll most likely do a future webinar on proper pump sizing and proper pump selection. So if we just go back and consider a pump system, there's typically 5 basic components that each pump system has. Obviously there's the pump or pumps. You know, if you consider the system, there may be multiple pumps in that system. Maybe they're in series, maybe they're in parallel. Along with the pump, there is a prime mover. Now typically that's an electric motor, although that is not always the case. You know, in some applications there may be a steam turbine operating the pump, but most of the time it's electric motors are the prime mover. Then in our system we have obviously piping, there'll be some valves, and then there's some end-use equipment. That may be tanks, heat exchanger, something like that, which is really, you know, the purpose of why we have the system in the first place. So if you're just looking at an example, here we have a cooling system where we have a fluid being pumped around a loop to a heat exchanger. Over here is our end-use equipment. That goes off to a cooling tower, and that goes round and round and provides cooling to this heat exchanger on the right. Now we've got obviously we've got our pump and our prime mover at the bottom here. There's a valve there to control the flow. Our end-use equipment, our heat exchanger. Usually there'll be some instrumentation and some sort of control system. Not always, but most of the time. And in this particular case, we have a thermocouple that is then using a control system to control the flow rate via this valve here. We have another end-use equipment here in the cooling tower, and obviously piping connecting the whole lot. And so if we only just consider the pump, we're actually losing the bigger picture of what the system is trying to provide. There is a function to the system, and in this particular case, it is to provide cooling to this heat exchanger. Now, just briefly, we can divide pump systems up into 2 main types of systems. One are closed systems. So these are systems that are closed, they're not open, meaning there is no static head change. So the only head requirement is that the pump needs to overcome are all the friction losses generated by all the components in the system. Okay, so all the pressure drop during because of the pipes, the valves, any end-use equipment, that's the only loss head that we have to overcome. Now this is fairly typical in heating and cooling systems. Most of those are closed systems, and what's really happening is that the liquid is used as the heat carrier, and heat is being transferred to the heat carrier, which is then being added or rejected somewhere else. And so we have our pump curve, which shows our head versus flow relationship, and then the red curve here is our system curve, and so that shows the head loss in the system as a function of flow rate, and where those two meet will be the operating point. The other type of system is what we call an open system. And so this may be, for example, where you have 2 tanks and you're pumping from one tank to another. And what you have to overcome here is obviously all of the friction loss again due to the pipes and fittings and things like that, but also any static head difference between the 2 levels that you're pumping from. So this is fairly typical of water transport, irrigation systems, and you'll find this at many other industrial processes as well. Maybe you're pumping water from the river up to use at your factory, something like that. And so there will be a static head requirement as well. And what that means is that your system curve, instead of starting at 0 head and 0 flow, there's actually the static head has to be overcome first before any flow will occur. So those are the two main types of pump systems that we have. Now, just to give you an example of why this is important to ask the question, what is the function of the system? If we consider this cooling system here that we saw before, okay, so we have our heat exchanger, we have our cooling tower, and our pump system is providing cooling to the heat exchanger. Now on the right here, instead of this red line here is our power curve. So that's the power consumption of our pump. And let's just say, for example, we're operating at this flow rate Q1. Okay, so at this point on the curve. And if we measure the temperature across the cooling stream, okay, let's just say, for example, that was designed that that cooling water was increased in temperature 5 degrees as it removed heat from the heat exchanger, and there'll be a corresponding flow rate depending on the duty that needs to be cooled. Now, at the moment in this particular case, if we put our best efficiency point on our curve, obviously this pump is operating away from its best efficiency point. Now, what we may do is we could decide, let's put a smaller pump on here or trim the impeller somehow to reduce the head requirement if we can, and then align it so our operating point is closer to our best efficiency point. Now that may be the case, we may be able to do that, but what we actually have to also consider is the heat exchanger. How large is that heat exchanger? We have to consider all the components in the system. Perhaps we might be able to operate with a larger temperature rise across that heat exchanger. So if we have a greater temperature rise in the cooling fluid, let's say to 10 degrees, then we can pump less water, achieve the same cooling, and let's say if we go to 10 degrees temperature rise, we will shift, obviously, we'll reduce our flow rate. That may be with a valve. We may get closer to our best efficiency point and reduce our power. And so without changing the pump, we've changed the operation of the system, and we've gotten a saving opportunity there because we're actually looking at the system. Can we operate the system differently and still achieve the same outcome? Now, obviously, you'd have to go through and do some proper analysis of the heat exchanger. Is the heat exchanger large enough to be able to operate in this manner? Is the cooling tower large enough to operate at this? Is the temperature going to muck things up for your cooling tower? And so maybe you can operate at a higher temperature rise in your cooling fluid, but also reduce, look at the pump as well to operate back closer to your best efficiency point. Okay, so there's typically some indicators of inefficient systems, and if any one of these things applies to your system, then the chances are it's worth having a look at, and we'll talk about how you narrow this down if you have many systems to look at. But first of all, typically if you have throttled pumps, so these are pumps which have a control valve which is fairly closed or not open for much, not fully open for much of the time. If you have bypass or recirculation flow, if that's occurring, then usually that's an indicator of an inefficient system, or there's some savings potential there. And so, Paul, I know you had a question about this, and I'll talk about this a little bit more at the end, if that's okay. But usually bypass or recirculation flow, there's some ways to reduce that and to eliminate it sometimes altogether. If you have large flow or pressure variations, then that's usually an indicator of an inefficient system, especially if that's coupled with a throttled pump. Typically, if you have a large variation in flow, then you should be looking at either variable speed drives or multiple pumps in order to provide the variable duty. If you have multi-pump systems, there's often optimization that can occur in order to give you a better outcome. If you have a system serving multiple end users, especially where minor users set the pressure requirement, then there are some optimization and control strategies that can help you out there. If you have cavitating pumps or valves, often that may be an indication that the pump is oversized, and so therefore there are some, that's a good place to look if you have pumps or systems where that is occurring. If you've got systems with high vibration, noisy pumps, pipes, motors, pump systems with high maintenance requirements, once again, typically oversized pumps have a higher maintenance requirement, and so that's an indication of an inefficient system, typically. If your systems have changed their requirement over time, whether that be pressure or whether that be flow requirement, then what may have been suitable when it was originally designed, it may now not be operating at its most efficient point, and so that leaves some room for improvement. And also systems where the flow and or the head delivered by the pump have degraded over time. That's often an indication that something's going on, something has changed, and there may be some potential to have some improvement there. Now, one of the things that is often not fully appreciated by many people is that if we just consider our pump curve here, our pumps will operate across a wide range of that pump curve. However, ideally we want our pumps to be operating at this best efficiency point, so the BEP. However, there's a preferred operating range where for long-term operation, we really want to operate our pump systems at the best efficiency point or within a very narrow range either side. And typically, people quote slightly different numbers, but typically between 80 to 110% of your best efficiency point of the flow rate at the best efficiency point is that preferred operating range for your pump for long-term operation. You can actually operate in a much wider range. It will happily operate within that range. However, if you operate outside of this preferred operating range longer term, then this will cause many other problems, which are not just from an energy point of view. Obviously, as you move away from your best efficiency point, your pump is operating less efficiently, but there are some other consequences for operating in that manner. If you operate outside of this allowable operating range, typically on most pump curves or most vendors will specify a minimum flow rate. And if you go below that minimum flow rate, you risk deadheading the pump, but you can then have some major things occur, such as high temperature rise in your fluid or major cavitation problems due to low flow. And so that's one of the reasons why bypass systems are introduced, is to avoid operating outside of that allowable operating range. Now, if we just carry on and talk about briefly the link between the operating range and maintenance reliability, we can actually put a reliability curve on this as well. And obviously, if we operate closest to our best efficiency point, we then have our highest reliability. If we operate outside of this preferred operating range between 80 to 110% of our best efficiency flow rate, what happens is we get non-ideal flow conditions occur within our pump, both the inlet and the outlet of the pump. So what starts to happen as you throttle the pump and you get outside of that, below that 80% flow rate, is the first thing that occurs is you start to have recirculation of the fluid at the discharge of the pump. Okay, so the outlet of the pump, there starts to be recirculation occur. As you continue to move away from that range, you also start to get recirculation in the suction of the pump. Okay, that then leads to lower impeller life because you start to get high levels of cavitation occurring because you have these high velocity vortices or recirculation zones, which then can cause cavitation. This then puts more pressure or more stress on the system, so that leads to lower seal and bearing life because you now have a lot more recirculation within your pump. You have low flow cavitation, starts to be a major problem, and if it's very highly throttled, so you go very much below your minimum flow rate for your pump, then you can have high temperature rise in your fluid. And if you just step back and think for a moment, you're putting energy in from your pump, and that is not going into moving the fluid through the pump because it's being restricted, and so that friction then ends up showing up in a temperature rise. And that can be a very high rate of temperature rise, especially for a large pump. And that's often, you want to avoid that. If we go to the other end and we exceed, or we go above the outside of the preferred operating range on the other end, we also see lower seal and bearing life, and we do start to have cavitation as well, although that's not due to recirculation, that's really due to our net positive suction head requirement. If you look at a pump curve, the NPSH required of your pump to operate, it starts to increase substantially and very quickly after the best efficiency point. And so that's where we can run into problems and have cavitation issues due to an NPSH problem. And we'll most likely talk about cavitation and net positive suction head in a future webinar. Now, in all of this, it's important just to remind us that life cycle costing is a really important method when comparing options that you're considering. If you're looking at replacing a pump, or especially a new pump system, is to actually look at a life cycle costing approach to begin with. Now, the initial cost of the pump obviously is important, and many companies, they put a big emphasis on minimizing capital cost. But if we look at life cycle costing, obviously there's the capital cost of the pump or the piece of equipment you're considering. There is a cost to commissioning and installing that equipment. Then there is the operational cost, the energy costs of operating that piece of equipment. There's the cost of maintaining that, and then there's also any downtime and lost production costs, especially that's relevant where you're looking at, say, replacement. Some options will take longer to implement than others. Now, typically for a pump and a pump system, around 40 to 60 or 50% of your total cost is actually in energy. So around half of your total cost of owning your pump is actually used in energy. Typically about 15 to 20% will be the initial capital cost of the pump, maybe 5% for installing and commissioning, and then maintenance costs over the lifetime of the pump may be as high as 25%. So what this means is that if we take a life cycle approach, it may actually be cheaper in the long run to make sure that our pump systems are operating efficiently, getting the correctly sized pump. Maybe it's worth spending a little bit more for a higher efficiency pump and doing it correctly, because over the lifetime of the pump system, that will then actually pay some dividends and some savings there. And there's some good examples that go through and show how to compare different options, and from a life cycle point of view, which which show the value in looking at this method. If you only look at capital cost, then you can end up paying a lot in the long term in energy costs. Okay, so there's a question about where is this life cycle cost data from. This is typically, it's slightly different for every system. This is from, I think this is from Pump and Systems as an example, which is like a magazine that talks about pump systems. There's some typically accepted average values for this sort of thing for pump systems. Obviously, that's going to be slightly different depending on the application, but for most industrial applications, it's fairly well accepted that about half of your total cost of your pump is actually in the operation of the pump. So hopefully that answers your question, Sam, but certainly for if you've got a particular system in mind, then you can work through the methodology and look at what your life cycle for your particular system is, and then compare different options. Okay, so let's talk about pump systems assessments and pre-screening. Okay, so if you look at, let's say at your site, you've decided that you want to look at your pump systems and make some improvements. The first challenge that you'll have is that you'll have multiple systems on your site. Now, I know of some sites in New Zealand that are very large that have sort of 800 to 900 individual pump systems on the site, from fairly small pumps to very large pumps. So you've got multiple systems on your sites typically. You also then have multiple sizes of pumps. They may be from sort of a kilowatt all the way up to very large megawatt size pumps. You'll have them for multiple uses, and you will also have multiple types of pumps as well. And so the key question is really where to start. And so this is where having a pre-screening stage can help narrow the focus and hopefully identify the pump systems with a high likelihood of having some savings opportunities there that will be economic to implement. Now, why is it important to narrow the focus? Well, if you're going to start a big assessment program, obviously you really want to find some early wins, get some runs on the board. What that does is, first of all, it can help economically justify more resources being put into an assessment program. It may justify more measurement, more monitoring, maybe some higher level analysis to implement a good solution. It also creates motivation to look harder and to work harder, and it may also, if you have a good project, help to provide motivation to look at other types of systems, say fan systems or something, to look at other energy savings opportunities there. Now, what I've done is I've sort of simplified a flow sheet from the ASME pump systems. I've sort of simplified it down, and what we're really looking at here is, if we decide we want to start an energy reduction program, then the first thing, or level one, is this pre-screening stage. And what that does is it helps us to identify some higher priority systems to then focus on and then do more in-depth assessment. What we may do with these other lower priority systems is actually develop policies and practices to look at how we improve those, but often there'll be a very long tail there, and some of them may not have any opportunities, but you may develop policies and practices such as, if a pump is going to be replaced due to a regular maintenance schedule, then maybe it's worth having a quick look and seeing, is there a better option there? So those sorts of things are fairly easy to implement and develop. But with the higher priority systems, and obviously that will depend how many there are, depending on how much work and your budget, etc. But then you can then proceed to higher level assessments of those systems. So level 2 I've just sort of called a snapshot assessment. So that's really using, existing data, not a lot of additional measurement. And what you're trying to do there is determine, is there an opportunity and do I have enough data to define a good engineered solution? And you're really trying to quantify savings and how do I implement that? Now, obviously, if you do have enough there, then you can develop an energy savings opportunity and then implement it. However, most of the time, especially for large opportunities, is it usually pays and is justified to do more in-depth analysis. So that's things like measuring of flow rates and pressure and power and things like that, and we'll talk about that a bit later. But what we're really going to focus on today is different ways of doing this pre-screening stage. Okay, let me just get rid of this. There we go. So the pre-screening stage, the goal or the purpose is really to sort the systems according to what the anticipated savings opportunities are. Now, before you do that, you really have to decide what is the purpose or what the objective of the assessment program is. Is it to simply reduce energy costs, or is it to reduce operational and maintenance costs? Maybe it's to increase production. There may be some other goal or objective of your assessment program. Now, why that's important that that's clear in everybody's mind is how you then screen, and the criteria which you use to screen on will be determined on what the primary objective is. And we'll go through an example of that. Now, the first thing to do really is to collect any data that is easily accessible. So things like piping and instrument diagrams, equipment data sheets, pump curves, things like that, and also having a chat to the plant staff, especially the maintenance staff. They usually have a good handle on, which are the bad actors, which pumps are continually in need of care and attention, and to collect that data as quickly as possible. Compiling an asset list is also very important. The pump, the type of pump, what's the nameplate on the motor, that sort of thing, what the operational hours of that pump system is, what the purpose of the system, and also the control method. That's quite important, especially if you want to narrow down your focus on only a few systems, and that can be very important. So getting that other information and then compiling an asset list is the first step. And so to focus on energy use and hours operation, that's really important. And we'll see as we go through the example that not only the size of the pump or the motor, but also the hours of operation has a big focus. That will change how these systems are screened. Also, pump systems that are controlled by throttling valves, bypass or recirculation, or that have no control, their often important to identify because, as we said before, they're typically an indication of inefficiencies in the system. Pumps that are operated at fixed speeds, they are prime candidates as well. Systems that have had major changes in design or operation since they were installed, they should definitely be included, and if you can find the original design criteria and what the current operational parameters of that system is, that's important to get. And also systems with high maintenance frequency or costs. Okay, so that's why talking to the staff is important, the plant staff, to get a handle on those sorts of factors. Okay, then what we can do is we can then come up with some attributes or quantities and then apply a weighting factor to that. And what that does is it then creates a score for each pump and each pump system, which then we can then do some screening on. Okay, so we're going to go through a quick example of this. And really, there's no set way. Your criteria or your quantities or attributes that you determine weighting factors for is really dependent on what the objective of the program is. So for example, here's my example that I'm going to go through. We have 7 pump systems here. I've just named them A, B, C, etc. And we want to, our goal of our program, let's say, is to reduce energy costs. That's really the focus. And we have a limited resources, so we actually want to just identify the top 3 candidates to do some more in-depth analysis of. The key in coming up with your weighting factors is to be consistent and apply them consistently. Okay, so these are the weighting factors that I'm going to come up with to do my pre-screening on. I'm going to, first of all, give a weighting on motor size. Okay, so anything above 300 kilowatts, I'm going to assign a weighting factor of 8. 100 to 299, 6, etc., etc. You can see from there. And then the second weighting factor that I'm going to apply is the operational hours of that pump system. Okay, so anything that operates more or less continuously, 8,000 hours or more, I'm going to give a weighting factor of 4. And then you can see the other weighting factors there for the other operating hours. Okay, so here is the information that we have for our 7 systems. We have our motor size, our operating hours, and then we can go ahead and we can put in those weighting factors, and we can add them together to get a total score for each pump system based on the motor size weighting factor and the operating hours weighting factor. Okay, so if we look at that, then our top 3 there are pump systems A, E, and G. And you can see that, you know, not all of the, we've got 2 pumps that are 500 kilowatts in size, not all of them make it into the top 3. Okay, this pump system D doesn't, and really that's because it has a fairly low operating hours there as well. However, if we then look at what the flow control method of each one of these systems are, then before we said to focus on pump systems that are throttled or that have bypasses. Normally, if there's a variable speed drive on a system, there will only be limited opportunities for savings potential, unless we address some other thing, but some other factors such as what the function of the system is. And so pump system A, we said before, that was actually on a variable speed drive to begin with. So even though it made it into our top 3 before, we can then go ahead and say, well, that's got a variable speed drive on. There's probably going to be limited opportunities there. Pump system D was very high on our list as well, and it had a bypass. So we're going to include that in our top 3. Pump system C also has the same total score of 8. However, that is also on a variable speed drive, and so that will have some limited opportunities there as well, potentially. So we can perform a very simple pre-screening that then allows us to identify the systems that we want to focus on in future. It may not be the top 3, you may have many more systems here. What you could do is assign a weighting factor also for your flow control method and score, say a throttled pump and a bypass system as a high weighting factor as well. Okay, so there's different ways. There's no right or wrong way to do this, but what you're really trying to do is to screen out by some criteria and identify the most promising candidates for future work. Then from there you would look at developing a further plan of action, looking at how to take these systems to the next level, level 2 assessment or level 3 assessment, where additional information needs to be gathered, and that may include some in-depth measurement and analysis of, say, flow, pressure or power if that's not available. Obviously, your system variability needs to be considered. That's an important part as well when you're looking at these systems. Developing the plan of action, obviously you need more information around the pump, the motor, etc., etc. That's needed after that. Now, just quickly, always be aware that there are barriers to implementation, and there may be several of them. And I know James talked briefly about these before, and so that we won't dwell on them. Okay, now we have a question by James Cameron, okay, about why not just look at your total kilowatt hours for your systems and then weight the flow control method. Absolutely, that's also another way. You could weight it for maintenance. You may have some other criteria that you're interested in. This was just to give you an example of how to come up with some weighting factors and then determine and then apply that to pre-screening. So the key, I guess, there, James, to your question around is really determining a method to pre-screen that suits the objective of the program. It may be weighting factors. You may just decide to do that on a kilowatt hour basis. Sometimes there's some uncertainty there. Sometimes the operational hours of your pump system may not be known very accurately, but as long as you're consistent and you have a method, the goal is to narrow down from several hundred systems down and identify the priority systems that you want to focus on. Okay, so in interest of time, we're just going to go to okay. Okay, so additional information. Where can you go if you need additional information? Well, first of all, a few years ago there was a ECA EMANS pump system audit standard, which has some information available there around pump system audits. Okay, there's the link there. That has some good information there. There's also an ASME, so that's the American Society of Mechanical Engineers. They have a energy assessment for pump systems. There's a standard, and there's also some guidance to that standard as well. The ECA systems audit standard is freely available. The ASME one is a paid standard, so you have to pay to get the standard. There's also a good article. There's a trade journal called Pumps and Systems, and there's a good article there that talks about the value of pre-screening to look at priority systems there. Okay, where to from here? We have some additional webinars in a few weeks. In 2 weeks' time, I'll be giving a webinar on industrial process heat, an introduction into that. Later in early November, Dr. James Carson here from the university will be talking about industrial process cooling. And then later in November, James Neal is back. He will be talking about steam systems and compressed air systems up until December. Okay, so the links there to register at our website, energyefficiency.nz.com, and also via the ECA website. Obviously, if this has piqued your interest, then ECA Business Program, talk to them, get in contact with your ECA account manager. Also, ecabusiness.govt.nz has some good information there as well of where to go. And as I said at the start, these webinars will be available to download. These are being recorded, and they will be made available via the ECA website in the future. So thank you for your attention. We've got some time for questions, so please feel free, if you have any questions, to send them through, and I'll answer them as best I can. Now, Paul from the steel mill, he had a question about bypass flow on pump systems. Now, as I said before, Paul, thank you for sending that through. James forwarded me on those pictures. Typically, bypass or recirculation flow was used to avoid deadheading the pump or to make sure that the pump was operating above the minimum flow rate. Usually, though, that can be achieved in other ways, especially if the pump, can be switched on or off. Sometimes there was just a set amount of flow sent back. So even when the pump demand was at its design point, there was still a certain amount recirculated back unnecessarily. But there are other ways of achieving this. Sometimes if it's really necessary, then you can have an automated or a control on the bypass. There's different ways of improving the efficiency of that if you can't get rid of it altogether. But certainly any system with a bypass on is a candidate to look at more closely. So hopefully that answers your question, Paul, but certainly we can talk to you about that a bit more. Okay, thanks, Pat. Any other questions, please send them through. I'll stay on the line for a few minutes longer. All right, Paul. So the question is, why are there fewer savings with VSDs? What a variable speed drive does is as long as you've integrated it correctly, opened your valves and things like that, you're using your variable speed drive to control the system, and so instead of changing the system curve to meet the demand, you're actually changing the pump curve to meet the demand. And so if that's done correctly, then you have a very efficient way of providing the head and the flow requirement. And so usually you have limited options unless you actually change the demand of the system. So for example, we had the the cooling system before, we had a 5-degree temperature rise. If that system was on a variable speed drive, we could change the set point of the system, say to a 10-degree temperature rise, and so we actually would then, the VSD would then control to that, and that's how we could get our savings. So savings won't come from putting a VSD on. It'll come from changing some other set point, and so usually, if you have a throttled system with a fixed speed pump, that's where your greatest opportunity is, not with a variable speed drive. But I guess the other thing I would say though, Paul, is that in the future we will have a webinar on flow control, and in particular the use of variable speed drives and where they're appropriate, and where they can give you the most value in your system. So hopefully that answers your question, Paul. Any other questions from anybody? All right, well, I think that's it. If you do have any questions or you want more information, please feel free to contact me or to contact Ika, and we can sort you out. So thank you very much, and I'll sign off now.